Hello friends, today we will study what is backtracking. Backtracking is an important concept in any algorithm designing and data structures. Backtracking always leads us to various choices which are not very perceptive when we are designing the algorithm. So, how backtracking is useful and where all the backtracking implementation is there, we're going to study. Now, backtracking is a concept. It is to make the series of decisions among the various choices. That is, if I make one decision, then it leads to one result. From that result, if I cannot go further, then I have to come back. That is a basic concept of backtracking. So, backtracking is needed when there's not enough information to know what to choose. That is, we have to make the decision on the basic minimum requirement of the information. Each decision leads to a new set of choices. When we make one decision and what follows is many more choices, and on that choices again we have to choose the best one. And if that best choice does not lead us to the real life solution, then we come back to our original problem. So that is a concept of backtracking. Some sequence of choices may be a solution to your problem, or it may not be a solution to your problem. Backtracking is a method, way of trying out various sequences of decision until you find the word works, that is, until it leads to a real world solution to your problem. So, backtracking plays a very important role in any algorithm design or data structure design. So, what we do next? The one simple example for backtracking is solving a maze game. Now, what is a maze game? Given a maze, we have to find the path from start to finish. From that start to finish, at each interaction of the maze, we have to decide whether between 3 or 4 choices, that is, the choices we need to make when we're trying to solve the maze game. Go straight, or we can go left, or we can go right. So, for a maze game, we need to have 3 choices. Now, these 3 choices can lead to a solution which will be either a perfect solution or we need to backtrack the solution. As we know, backtracking is needed. Why? Because not enough information is needed correctly to choose whatever we need. Each choices lead to another set of choices. If we go straight, then from that straight also we'll have again 3 choices where I can go straight, I can go left, or I can go right. Or if I choose left, then at that left position, again I'll have 3 choices which will tell me whether I can go straight, I can go left, or I can go right. And same proposition exists when I choose the choice right. And one or more sequence of choices, as we've spoken, may lead to a solution, or it may not lead to a real world solution. And many types of maze problem can be solved using backtracking. So every time I choose a solution, if that particular solution does not lead me to a perfect real world solution, then I need to reconsider the solution that I traced at a previous fixture. So in the previous step, I reconsider, or I retrack, or I backtrack my algorithm. So in the backtracking of algorithm, it always leads that my solution will be a newer one with a good choice. So what happens next? We need to solve this particular problem. One is solving a maze. The second important thing which the backtracking considers is a coloring a map. Now, coloring a map is a very simple example where we need to consider that no 2 colors should collide with each other. That is, whatever boundaries we have, all those boundaries of colors should be different. If we see over here, the boundaries that we have created for colors, they are all different types. We have taken red, brown, purple, green, yellow or blue. All these different colors should map separately. If I have to choose any color twice, then the color should not come next to each other so that it will be submerged with each other. So we need to consider backtracking in this case. So what we do, to color a map with not more than 4 colors, let's assume that any given map we will be mapping with only 4 colors, that is red, yellow, green and blue. Adjacent countries or adjacent areas may not be in the same color, that is, they must be in the different colors. Not enough information is again available to choose, as we do not know what color each country will be given, but we have to be very sure that whatever color we give to a particular country or particular area, the boundaries at which it is fixtured will not be of the same color in the next boundary, and each choice will lead to another choice. If I color the first boundary as red, then the next boundary in that particular area should not be colored with red, and one of the more sequence of choices will lead to another solution. And many coloring problems can be solved with backtracking. And then there is solving a puzzle with backtracking. These are the few examples of backtracking that we are considering. Now, this is a simple puzzle where in this puzzle all holes but one are filled with white pegs. That is, the center hole is black but rest all pegs are white in color. We have to jump over one peg with another peg, but it should lead, as we jump the peg, they are removed. So we have to be very careful that when we remove all the pegs, in the end, we should be left with only one peg. And jumping should be such that there has to be a peg in between for us to jump over it. When we jump over a peg, then only we can remove the peg. So what happens is, if we keep solving this problem on a playing board, then it can be easily solved. That is, if we cannot do it, then we keep retrying it. But for writing an algorithm, data structure or a program code, we need to work on this in a backtracking proportion. And backtracking proportion works perfectly when I have a recursion working with it. So the backtracking is implemented well with recursion. This is a backtracking example for an animation. Here are the few examples that we are considering where backtracking can be implemented. So here what we see is we start off at a position where we do not know anything in the animation part of it. So it leads to another issue or another animation frame where we've reached a dead end. So after we reach a dead end, we come back to a screen where we depart or we take a second step, which is again a dead end. And if you see, we have put a question marks at 5 places, and at all these 5 places only one question mark leads us to a success rate. The last part, after configuring all the animation issues, leads us to the success. And here if you see, it goes like this. If this leads to a dead end, then we backtrack it to this dead end, and when we revert, then what happens? From this question mark we come back to this, and this has a newer choices which comes over here, and this newer choices leads to a dead end again. And this dead end, if cannot be reached or solved, then we resolve it over here to another choices. From these choices we reach to many more solutions, and in the end we reach to a success part where we say this animation backtracking has given us a successful output. Now we see what is tree backtracking. Now what is a tree backtracking? There is a root node. To that root node there are various parents below, and for those various parents there are children. And when we're trying to either have a pre-order, post-order or an in-order traversal, or for a binary threaded tree, I need to have a traversal. Then we need to do backtracking for a tree. A tree is generally composed of nodes. And if this we consider as a tree, if you see the green one is root node and the yellow ones are the parent nodes and the red ones are the leaf nodes. Then for this tree, how a backtracking works. Now, when we consider this tree, then let's see what are the nodes. There are three kinds of nodes which are existing for this particular tree. And these nodes are green color, the root node. The yellow ones are the internal nodes or known as the parent nodes. And the last ones, the red ones, are the leaf nodes. That is, from the leaf nodes, these are the children from where we need to backtrack. And the upper node is known as a parent node and the one at the top is a root node. So what happens? Backtracking can be thought of as a searching a tree for a particular goal, that is leaf node. If I need to track or if I need to solve a particular node in a particular tree, then what do? I search usually from my root node to the parent to the left side of the child, and I traverse in the left of the tree. That is known as a left child traverse. And if that particular node is not found in the left side traversal, then I go to my right side. If you see a tree over here, it is a general tree as one parent has more than two children. And any tree, if it has only two children, then it is known as a binary tree. But in this case, my node has three children. So this is a general tree and not a binary tree. So for any general tree also, I traverse first on the left hand side and then check the middle and then check the right part of it. And if my desired data is not found, any of the first traverse child nodes, then we backtrack to the parent and then backtrack and above. So this is how my backtracking works for a tree backtracking. See, now next is each node, that is non-leaf node in a tree, is a parent of one or more other nodes are its children. If it has leaf nodes, then that particular node is known as a parent node. And then each node in the tree other than the root has exactly one parent. So root node being the basic will not have any parent on top, but any other nodes that follows will have a parent. As for the first node, if there are two nodes down, then the root node only by itself serve as the parent for that particular node. And see, here it is, that is the parent, one node, and the three nodes which follow below are known as the children. Usually, however, we draw trees downwards with the root at the top. The root node always remains at the top hierarchy and then follows in the next level is the parent, and the level below are known as the children. So we usually draw it in the hierarchy of parent and the children following below it. So now we have to see that how my tree backtracking will help. Now what are the real and what are the virtual trees? If you see, there's a type of data structure called tree. So tree is nothing but a data structure of an algorithm which can be implemented in backtracking. So what happens? But we're not using it here. So what are we doing? If we diagram the sequence of choices we make, the diagram looks like tree. Our backtracking algorithm sweeps out a tree in our problem space. Now backtracking is very simpler algorithm implementation where the tree implementation comes into picture as we have to backtrack any choices that we have made. So we say that it follows a tree structure, and that tree structure is not an actual real life tree structure, but we consider it as a virtual tree. So whatever backtracking that we do will be a virtual tree backtracking, as there will be a parent node which will be my previous decision and a previous choice. On that previous choice, when I make a decision and come below, those are my children. If my children leads to my real life problem, then it leads to a virtual tree solution to a backtracking. Backtracking is really quite simple as we explore each node as follows. These are the few steps that we're going to consider while we are doing the backtracking algorithm. To explore a node n, what we do are the steps. If n is a goal node, we return success. That is, we have reached to a successful real world solution. So there's no need of backtracking getting implemented. And if n is a leaf node, then we return a failure. That is, we have not reached a success, but we have reached the end of the tree node, or end of the road or the path from where we cannot lead further, and we have not reached a real world solution. So we start backtracking it. And for each child C of n, that is, we have this component called C for where we have to explore. We explore C, and if C was successful, we return success. And if C is not successful, then we return failure. And once we return failure, then this algorithm steps will be repeated in a recursive manner for us to give us a backtracking real world solution. So what we have to do? We have to consider this algorithm for map coloring again. The four-color theorem states that any map on a plane can be colored with no more than 4 colors, so that no two countries with a common border can have the same color. As we assume in a two-planar that each country or each plane that we have has 4 boundaries. So what we do, we have 4 colors, so no 4 colors, so no 2 countries, or no 2 planes, or no 2 areas will have the same color in that boundary. So that is how the map coloring implementation comes into picture for backtracking. For most of the maps, finding a legal color is easy. For some maps, it may be fairly difficult to find the legal coloring. Why? If my areas are very small and which are linked to those boundaries, and we are using only 4 colors, so it becomes little tough for us to map those colors to the boundaries. So at some situations, backtracking will be really important, as we need to map the colors in a recursive manner. So when I have to backtrack and map the colors in the recursive manner, then the data structures come into picture. What data structures we need to implement when we are implementing backtracking? We need a data structure that is easy to work with and which supports lots and more common algorithms. Setting up a color for each country. For each country, finding all adjacent countries. If I have set up the color, for example, was red, and all the adjacent countries which are sticking onto it cannot be given a red color, but it should be given any other color, that is blue, yellow or green, and but not the red color. So we have to be very careful when we are working on the data structures for this particular map coloring algorithm. We do this with 2-dimensional arrays. We take it as a simple algorithm, as the simplest possible form of data structure to implement a 2-dimensional array. One will be the array of colors, where the country color I is a color of the ith country. Let there be n number of countries, but for any country of I, that is, I can be varying for the number of countries that you put in your array. So for the any ith country, the color will be stored in the country color I array. Another rugged array of adjacent countries is taken, where the map ij will tell at which location the country is stored. And for any array of adjacent country, the map ij, the jth location of the country is stored for that ith country to which it is mapped. Example, when I say map 5 of 3 is equal to 8, which means that the third country adjacent to the 5th country is the 8th country. So to the third country, the mapping area of the 5th country, when both of them map, then it leads to the country that is known as the 8th country. We saw the example that if we take map 5 of 3 is equal to 8, then we say that the third country adjacent to the country 5 is the country 8. This is how the coloring algorithm or the coloring mechanism will follow for each country. Now, how do I create the map for the same? Now, for creating the map, if you see, this is how it has been created as 0, 1, 2, 3, 4, 5 and 6. These are the areas that have been defined. Now this is a very simple algorithm data structure which has been written. When I say create map, the map 0, that is called as the new integer, has the areas which are touching it are 1, 4, 2 and 5. So map of 0 will store what all areas? It is storing 1, 4, 2 and 5. Now 1, 4, 2 or 5 are very clearly stated that those are the areas which are touching my 0th map location or my 0th country. When I say map 1, what are the areas which are touching? If you see, it is the 0th one which is touching, the 4, the 6th one. Why the 6th one? Because the 6th one and the 5th one, as it touches a single part of it. Somewhere when I go to the 6th one, that is touching the first one. And when I say 2, 2 has been touched by the 0th location, the 4th one, the 3rd one, the 5th one and the 6th one. A small part of it is also touched by the 6th one. So this is how we differentiate the different maps of the countries. If you see the map of 3, then at 3 it has been touched by 2, 4 and 6. And if you say map of 4 is touched by 0, a part of it, 1 on a larger structure, 6 again on the larger structure, 3 on a larger structure and 2 a small part of it, but it is still touching. So I cannot have the same color for the 4 as it has been touched by all this. So I have to work and backtrack on the color scheme of these 3 or 4 maps where it has been held. And now when I say map 5 is held by 2, 6, 1 and 0. So the map color 2, 6, 1 and 0 are held with this map country 5th. And the map country 6 has adjacent numbers as 2, 3, 4, 1 and 5. So this is a create map which has been created for this particular countries, and we can see that for each country or for each labeled area we have found out what are the boundaries which are touching these areas. Now how do we work on it? We have to set up the initial colors. Now when it is 0, it means there are no colors, and the final starting value, the red gets a value 1, yellow 2, green 3 and blue 4. But initial map colors to all are set to 0. Now backtracking, why is it essential? And let's have a glance of it. Now backtracking at a glance means I need to consider why I needed backtracking as an important note. Backtracking, let's see why we needed as an important note. Let's have a glance at it. We went through all the countries recursively, starting with country 0, and we saw how each country was linked or mapped with another countries. At each country we have to decide a color. We decide the color for each country and it had to be different from the adjacent countries. So we had to follow a recursive manner so that we can decide what is the color of the country code so that it leads us to the best solution. And when it leads us to the best solution, then the adjacent country code is decided. And when we decide the adjacent country code, then only we proceed further. And if we could find a legal color, then we report it as success. And if we cannot find a legal color, then we report it as failure. And if at any point of time we report the color code for the country as failure, then we have to backtrack. And if we cannot find the color we used it and reoccurred in the next country, then we do backtracking. If we ran out of the countries, we colored them all and then we reported them as success. So the backtracking becomes very essential in this case when I'm coloring the countries with different colors. So when I do a backtracking essential algorithm, I have to check with each country. Thank you.